Hi guys, welcome to Geeks for Geeks. In this video, we are going to discuss about the binary representation of a given number. The problem says that given an unsigned integer, say n, and we need to print the given integer in the binary number system. For example, if n equal to 6 is given as input, then its binary representation comes out to be 110. And if n is equals to 58, then we see that it has a binary form as shown on the screen. Now, how can we do this efficiently? Well, we would discuss two approaches here. The first one is the iterative approach, and the second one is the recursive approach. Let's go with the iterative approach first. A simple approach which comes first in mind is to go through every single bit in n from the most significant bit to the least significant bit and print them as it is. We check ith bit by taking its bitwise AND operation with the 2 raised to the power of I. Let's go through the code for this approach. Here we have a function named bin which takes an unsigned integer n as an argument. We first take another unsigned integer I and run a for loop that iterates over the binary bits from MSB to LSB. The loop begins with I equal to 1 left shift 31, that is a 32-bit integer with only its leftmost bit as set. And the loop ends at I equal to 1, that is a 32-bit integer again with only its rightmost bit as set. In each iteration, the position of the set bit in the integer I checks the corresponding bit in the given integer and print 1 if it is set and else print 0. Here it is assumed that we are dealing with the 32-bit integers only, although the concept may be extended to any number of bits. The complexity analysis of this approach is as follows. Since we check and iterate for each and every bit in the given integer n, the time complexity for this algorithm is theta of log n. And since our space remains constant throughout, the space complexity is big O of 1. Now let's watch out the recursive approach for solving the given problem. Here we make the recursive function which calls itself for the each bit in the given integer. This goes in two steps. In the step 1, we first push the number onto the stack and call the same function for the number divided by 2. This continues till the number is greater than 1. And now in step 2, we examine each element from the stack and print the modulo of the number divided by 2 till the stack becomes empty. Let's understand this with example. Here we have an integer n equal to 10 having the binary representation of 1010. Also, the recursive stack is initially empty. Now, since 10 is greater than 1, we push 10 onto the stack and call the same function for n equal to 5. Again, since 5 is greater than 1, we push 5 onto the stack and call the same function for n equal to 2. Still, we see that 2 is greater than 1. We thus push 2 onto the recursive stack and call function for n equal to 1. Since now n has become equal to 1, we just push 1 onto the stack and move to step 2 of our algorithm. In the step 2, we just pop each element from stack and print the modulus of each number with 2. For example, 1 modulo 2 is 1, 2 modulo 2 is 0, 5 modulo 2 is again 1, and 10 modulo 2 is 0. Thus, we get 1010 as the output, which is same as that being shown earlier. Let's now quickly go through the code for this approach. Here in the recursive function termed as bin, we take an unsigned integer n as an argument. Then we first check whether n is greater than 1. Then according to step 1, we call the same function, that is bin of n divided by 2. When n becomes less than or equal to 1, we enter into the step 2 and print the number modulo 2. Here it should be noted that the stack is implemented using the recursive function calling. Now can you guess the complexity of this approach? Here the recursive function calls itself for the number divided by 2. And dividing any number by 2 is actually equivalent to right shifting the number by 1. So we can say that the function calls itself the number of times equal to the number of bits present in its binary representation, and n has log of n number of bits. So the function takes the complexity of the theta of log n in time. Meanwhile, we also need a stack corresponding to the number of bits of the given integer. Thus, this makes our space requirements grow at the order of log n as a space complexity also. That's all for now. Thanks for watching. Please leave us your comments.